In this lecture, I will explain you pulse position modulation. So we have already done PAM, PWM, and now the third one is PPM. So when I am speaking about PPM, then I will write position of pulse varies according to the modulating signal, because I am talking about the PPM. So position of pulse varies, and PPM can be derived from PWM. We can derive this from PWM. So when we are talking about PPM, that means what does it indicate? We are talking about the position of the pulses. Okay. Okay. Now in this case, okay, let me block this first. Generation of PPM, again same, the generation and detection. So I will talk about the generation of PPM first. Okay, generation of PPM signal. So there is one block. Again, it's a converter. We already did the converter. In comparator, it has two signals, two terminals, the positive and the negative. On this positive terminal, what we have given? Input signal. And on this negative one, what I have given? What is the input? Sawtooth signal. Okay, like in the previous one. So input signal will be the modulating signal, as simple as that, and the sawtooth signal will be the carrier signal. Okay, and then this will give me PWM as we did earlier, and this will pass through monostable multi vibrator. Okay, this will pass through monostable multi vibrator, and this will give me PPM signal. So this is the block diagram, and I'll do the explanation here. At every falling edge of PWM monostable multi-vibrator, output goes high. Okay, and second, it remains high for fixed time decided by its own RC components. Okay, I'll explain you now this thing. Okay, it remains high for let me just convert it, for fixed time decided by its own RC components. Now first of all, before explaining that, I will explain you what is monostable. Okay, monostable, as its name indicates, mono means single, so it has one stable state. It has only one stable state, and that is low. Okay, if we give a trigger pulse, okay, if we give a trigger pulse, then output becomes high for some time, not always, it will for some time. Okay, means, let me explain you here. So let us say this is the multiply vibrator. Then who will decide the output will be high for how much time? Okay, so monostable multivibrator has R1C components which decides. Basically what happen is monostable multivibrator has only one stable state, which is the low state. Okay, but when we give a trigger pulse, that means output becomes high for some time, and then basically what happens is it has R and C components. So what does this R and C components? They decide like for how much time the output will become high. Okay, so this is the function of monostable multivibrator. Okay, so this is the explanation of monostable multivibrator. I'm just blocking it like this. Okay, so I can ask in the exam, what does that mean? What does that mean having monostable multivibrator here? And now in explanation I have written at every falling edge of PWM. Okay, there are two edges, falling and rising. Okay, at every falling edge monostable multivibrator goes high. So suppose this is the waveform like this. So this is the falling edge and this is the rising edge. Okay, let me explain it nicely. Suppose this is a pulse like this. So whenever it is going high, this one, so this is the rising edge. Okay, and now it is going low, that means it is the falling edge. So at every falling edge the output becomes high. Okay, it remains high for fixed time decided by its own RC components, and then again it becomes low. Okay, so you need to remember this, and then I am making the waveform. You will understand it better with the waveforms. Okay, okay, if I am making the waveform, suppose let us say this is PWM basically, right? I have PWM signal. PWM means width is not constant. It can high, it can low, anything. Okay, so you can see the width is not constant. So I can write this output is PWM output. Why this is PWM output? Look, first of all, the input signal, the modulating signal, sawtooth signal, they are going through the comparator, and it is giving the PWM output, and then it goes to the monostable multivibrator, which gives us PPM signal. So now this signal goes to the monostable multivibrator. So what we'll do, I will just make a dotted line on the falling edge. This is the falling edge. See, this one is the rising edge. This one is the falling edge. So I'll just make the dotted line on the falling edge like this. And then see what it is written here. At every falling edge of PWM, monostable multivibrator output goes high. So it will go high. It remains high for fixed time decided by its own RC components, and then it becomes low. Okay, so what I am doing is at every falling edge, see at this one I am making it high. It will be high for some time and then it will become low. Okay, and then again it will be low till the falling edge of the next one. Then it will become high for some time like this, and then it will become low. Then again the falling edge, it will become high for some time and then again low, then again low like this. Okay, so now it is the PPM signal. So you can see that the width is constant but the position is not constant. Okay, so you can see the distance between them is not constant. Okay, and this pulse width is decided by RC of monostable multi-vibrator. Okay, that means the monostable multi-vibrator has the RC components and the width is decided by this. Okay, so remember, when xt is low, distance between pulses is low. When xt is high, distance between pulses is high. Okay, so you need to remember this. So it's very simple. You need to just remember the block diagram and these two statements, functioning of monostable multivibrator and the waveforms. Next is demodulation of PPM, pulse position modulation. Okay, demodulation. So for demodulation, there are blocks. The first one is pulse generator. The second block is reference pulse generator, and then it goes to a flip-flop. I don't know if you studied the flip-flop in your digital systems or not. If not, then you are going to study it. This you will study in your digital systems. So this is R, this is S, and this is Q. Okay, I will explain you what is this. And next is PWM demodulator. Okay, and here is the input PPM pulses, and next is here reference pulse generator. So basically for demodulation of PPM means what basically I need the main modulating signal, the message signal I require. Okay, so now in this case we are using this flip-flop. So this is SR flip-flop. So this you will study in your digital system. So it has two inputs, one is R and one is S. So R is basically reset and S is basically set. And there is one output of this block which is Q. So this is your output. Okay, so this is the explanation of SR flip-flop. Details you will study in your digital systems. Okay. So what will happen is corrupted PPM to clean PPM. This PPM goes to the reset pin. So this is basically the corrupted PPM. Okay, we get the corrupted PPM and this PPM goes to the reset pin of this, and then reference pulse generator. This creates the constant width and pulse with constant delays to the set pin. Okay, so I am explaining it and I am writing it so that you understood. The first point, what it will happen, the corrupted PPM. Corrupted PPM means the PPM with the noise or anything. It will become clean PPM first. This PPM goes to reset pin. And then what reference pulse generator does? Reference pulse generator, it will create constant width and pulses with constant delay will goes to the set pin. Okay, so on reset pin PPM goes there and on set pin Pulses with constant delay goes there. And after that, the output goes to PWM demodulator and it will gives the correct XT. Okay. So this is basically the explanation. Next is your advantages. Advantages of PPM. So the first one is low noise interference as compared to PAM. Second is noise removal. Noise removal and separation is very easy. The third one, power usage is low. Okay, so these are some of the advantages of advantages of PPM. Okay, second is disadvantages. Disadvantages of PPM. So it has synchronization between transmitter and receiver is required. And second is large bandwidth is required for transmission. Okay, so these are the disadvantages. Large bandwidth is required, which is the major disadvantages. As you have seen, it is disadvantage in each and every case. Okay, and synchronization between transmitter and receiver is required. Okay, next is applications. Where it is used in RF communication, and second is also used in contactless smart card, HF tags, etc. Okay, so whatever tags you are using, whatever smart cards you are using, so this technique is used in this one. Okay, so this is all about your PPM. So till now we have covered all these three techniques: PAM, PPM and PWM. The generation, the block diagram of the generation, the block diagram of the detection, and advantages, disadvantages and applications. Okay, so in your exam this question will come in 10 marks for everything.